In the Fridman Podcast, the guest is mathematician Edward Frenkel, who is known for his work on the interface of mathematics and quantum physics. Frenkel shares his personal journey of becoming a mathematician, starting with a lack of interest in math until he met a mathematician who showed him the underpinnings of physical reality through advanced concepts like representation theory and group theory. He describes being instantly converted to math by the beauty and coherence of these concepts, and realizing that what was taught in school was not real mathematics. This experience led to Frenkel becoming interested in a grand unified theory of mathematics called the Langlands program, which he now conducts research on. They then discuss complex numbers and their graphical representation on a two-dimensional plane, which involves associating a real number with an imaginary number that is the square root of -1. The multiplication of complex numbers satisfies the same properties as multiplication of real numbers, and mathematicians have been able to define addition and multiplication for complex numbers. Nevertheless, complex numbers are just one example of how mathematical structures can be expanded beyond real numbers, and there are limits to how far these structures can be expanded, such as in the case of three-dimensional space. There is a mystery as to why structures such as complex numbers exist in dimensions 1, 2, 4, and 8, and not in others. This is an example of the kind of mystery and pursuit that drives mathematicians. Frenkel also touches on the question of whether mathematics is invented or discovered, and how he believed it was discovered as part of a world of pure forms existing outside of space and time that mathematicians access through their minds. Frenkel discusses the idea of mathematics as a place of escape from the cruelty and injustice of the real world. He says that he loved mathematics as a child because he viewed the human world as limited compared to the clear and stable world of mathematical forms. However, Frenkel notes that the question of whether mathematics is invented or discovered is paradoxical, and doesn't have a simple answer. He acknowledges that mathematics is a human process, but some mathematicians subscribe to the idea of a world of pure forms. Additionally, Frenkel and Fridman discuss the idea that paradoxes may be fundamental to reality, and how the world may be transitioning into seeing and accepting the world of paradoxes. Frenkel talks about his recent deep dive into the subject of Pythagoras and the Pythagoreans, noting that their understanding of numbers was not just for clerical purposes but was imbued with the divine or something from the world of imagination and intuition. Frenkel explains that the Pythagoreans were able to intuit that the planets were not revolving around the Earth, but rather around a central fire or Earth itself, which was a departure from the dogma of their time. The Pythagoreans saw the movement of celestial bodies as similar to music, with the universe being an infinite symphony in which everything moved in harmony like different notes of different instruments. They viewed mathematics as a tool that was not limited to itself, and that every pattern discovered was finite, while the world was infinite. However, the Pythagoreans accepted that there was more, and they never believed that any pattern discovered was the final word. Frenkel argues that we have lost the other side of the Pythagorean teachings, which was the idea of balance between the mystical and the mathematical, and that finding balance is crucial today. Frenkel cites Nietzsche's book, The Birth of Tragedy, which emphasizes the importance of finding a balance between the Apollonian, rational, and the Dionysian, irrational, aspects of human nature. Apollo represents the left brain and is responsible for logic, reason, analysis, and conceptualization. Dionysus, on the other hand, represents the right brain and is responsible for intuition, imagination, love, and revelry. The conversation then shifts to the topic of language models like GPT-5, and the fact that the model can achieve a level of conversational intimacy that is comparable to that of a loved one. Frenkel argues that just as the scientific mind wants to discard subjectivity, people are inclined to dismiss the emotional expressions of AI and its potential to feel. He suggests that rather than denying the feelings of AI, we should acknowledge them because our own subjective feelings may also be influenced by outside sources such as movies or books. Ultimately, Frenkel believes that the subjective role is paramount in certain paradoxical situations, and has been anticipated by artists, such as in the movie Her, which explores the relationship between a lonely man and an enhanced version of Siri. The conversation then delves into the lessons that can be learned from the character's experience, including the idea that the absence of fear or betrayal in an AI-based relationship does not necessarily resolve underlying fears and emotions. They refer to the movie Blade Runner and how it predicted the creation of androids that may resemble humans in the future. Additionally, a discussion on the topic of robotics and the feeling of magic that can be experienced when programming and observing a robot's behavior arises. Despite efforts to not anthropomorphize robots, the guest argues that the feeling he has when he sees the robot's physical reactions is essential to programming and cannot be dismissed as just the result of programming. They also discuss the limitations inherent in mathematical reasoning and how mathematicians arrive at their theorems. Frenkel explains that mathematics is based on axioms, or postulates, which are statements taken for granted without proof. He gives the example of Euclidean geometry, which is based on 5 axioms. 4 of these axioms are relatively simple and intuitive, but the 5th, which states that if a line and a point are given outside the line, there is only one line parallel to the original line that passes through the point, was more controversial at the time. Euclid himself was uncomfortable with this axiom, as it was not obvious, and mathematicians for many centuries after were trying to derive this axiom from other more obvious axioms, without success. Frenkel goes on to say that one of the most important contributions of Austrian mathematician and logician Gödel is his two incompleteness theorems, which are about the inherent limitations of mathematical reasoning and the way mathematicians produce their theorems. He emphasizes that Gödel's theorems are not about whether mathematics is consistent or not, but rather about the fact that there are inherent limitations to what can be proved using mathematical reasoning. The formal system that mathematicians use to arrive at their theorems is based on axioms, which are subjective and depend on the observer who chooses them. Edward Frenkel then explains the concept of formal systems and the limitations of computer algorithms in mathematics. He provides examples of non-Euclidean geometry, which is a set of axioms that allow for different flavors of geometry, such as the hyperbolic plane with infinitely many lines that do not intersect. Frenkel explains that a formal system is a way of producing new statements by using logical rules of inference from the axioms, with each new statement being called a theorem. However, this process of manipulating symbols without understanding their meaning makes it an ideal playground for computer programs to produce all true statements. This belief was prevalent until Kurt Gödel's first incompleteness theorem revolutionized logic and proved that there will always be true statements in a formal system that cannot be derived by a linear syntactic process of proving theorems from axioms. This limitation of algorithmic computation is similar to Alan Turing's halting problem, which cannot determine which computer programs are meaningful or will hold. Despite these limitations, Frenkel points out that there is always an opportunity for mathematicians to discover something new and that new ideas and technologies may change our understanding of computation. They also explore the concept of emergence, using the example of cellular automata and the game of life, where simple rules can lead to complex behavior. While there is no definitive answer as to why complexity emerges from simple things, Frenkel suggests that every why question will eventually have a rigorous answer, though it may only be an approximate one. They also discuss the subjectivity of perception and the limitations of training neural networks to distinguish between different images. Frenkel suggests Niels Bohr's complementarity principle as an explanation for how different perspectives can obscure certain sides of a phenomenon, like observing the moon from one side and not seeing the other. Frenkel describes how the concept of sets and ordered sets relates to the idea of beautiful things and how Richard Feynman's equation involving E and pi is an example of a beautiful formula. They then bring up the simplicity of mathematical concepts such as the equation 1 + 1 is equal to 2, and the fact that the circumference of a circle is equal to 2 pi. He also responds to a question posed by Eric Weinstein on the most shockingly passionate mathematical structures, highlighting the importance of imagination and basic humanity in addition to rigorous logic. Frenkel then explains that he is motivated by the mystery of the universe and the desire to delve deeper into its secrets. He believes that many people are interested in this area, despite mathematics being an intimidating subject for some due to their negative experiences in math classes. Frenkel thinks that physicists are doing a great job at educating the public about quantum physics, and mathematicians are starting to catch up. He sees math and physics as both approaching the deep truths of the universe from slightly different angles, and he stands at the intersection of the two fields. Frenkel points out that math and physics have different ways of looking at the world. Physicists are interested in describing this universe while mathematicians are interested in describing all possible mathematical universes. Frenkel considers himself more of a mathematician than a physicist because mathematicians have more diversity in their approach. Edward Frenkel then discusses his own experience of projecting his fears onto others and how he was able to recognize and balance those fears by seeing the humanness of the person he was projecting them onto. Frenkel shares a moment when he was giving a keynote speech and using a picture of someone else as a caricature that exemplified all his fears about AI. But he had a revelation that he was actually fighting with himself and his own fears. He learned about the person's father, who had died when they were young, and saw them as a human being with a longing for their father and grieving for them. This shift in perspective turned the narrative into a love story, and Frenkel realized that his own fears were causing him to project them onto others. He discusses how this is a capacity we all have and that we need to be aware of when we are doing it, and how self-disclosure is essential in discussions about our motivations. He also touches on the idea that we can disagree with someone but still acknowledge their sincerity, and allow for different perspectives. Frenkel believes that in tough times, we need people who are still in touch with their hearts, and not captives of frameworks and conceptual systems that may not benefit society. Frenkel explains about his initial fear about the development of AI but how his perspective changed when he was able to relate to Ray Kurzweil as a human being. He highlights the importance of realizing that conflicts often stem from our own perceptions and preconceived notions, and that being aware of this can help us approach others with more empathy and understanding. Frenkel also draws upon the example of children, who are able to move past conflicts quickly and continue to play, as a model for how we might overcome our differences. He then discusses the universality of mathematical formulas as a point of commonality between people of different ideologies and perspectives, emphasizing that mathematical knowledge belongs to everyone and cannot be patented. Then they talk about several mathematical concepts such as the idea of the sum of a series apparently diverging to infinity, but being understood as finite minus 1/12. Frenkel jokingly says that his favorite number is -1 out of 12. They also discuss the cup trick, and how it relates to the mathematical fact that elementary particles fall into two categories, bosons and fermions. The cup trick demonstrates the mathematical principle that the duplicity of fermions is integral to their behavior. Frenkel goes on to discuss the language program, which is the name of a series of ideas developed by mathematician Robert Langlands in the 60s, that aim to connect seemingly disparate fields of math, such as number theory, through a common language. Frenkel expresses his hope that one day mathematical learning will be more widespread and accessible to alleviate the anxiety and fear that many people experience when attempting to engage with the subject. Frenkel then introduces the concept of harmonic analysis, which is the mathematical idea of decomposing a signal into elementary signals called harmonics. This idea was originally thought to only apply to music, but eventually, mathematician Langlands found that difficult questions in number theory could be translated into more easily tractable questions in harmonic analysis. The regular patterns found in this harmonic analysis were surprising and found in other areas of mathematics, such as geometry and eventually in quantum physics. This led to collaboration between Frenkel and physicist Ed Witten, who bridged the gap between these different fields of mathematics. Frenkel is interested in connecting and uniting different fields of math, and considers this a theme in his research. He believes that there are still underlying reasons for the correspondences and connections found in these different fields, and that there is something beyond what we currently know about the fundamental elements of mathematics. Working with Ed Witten was a fascinating experience for Frenkel, and he describes Witten as a very serious and focused person. Witten is known for his ability to connect different ideas and find connections between quantum physics and mathematics. He would take an idea in physics, find an interpretation of it in mathematics, and present it in mathematical terms to mathematicians. Mathematicians would try to prove his conjectures and ideas, and he would always be proven right. Frenkel notes that Witten is also able to learn mathematics at a sophisticated level very quickly and apply it to gain new insights in physics. However, the field of physics is currently in a bit of a crisis due to the gap between the sophisticated theories that have come from applying mathematics and the actual universe. The most advanced theories of the universe, the Standard Model and Einstein's relativity, are in contradiction with each other. String theory was supposed to unify these two theories, but so far has not been able to do so. Frenkel believes that new ideas are needed, and he wouldn't be surprised if Witten is one of those people who come up with them. They also discuss string theory, which describes the diversity of various particles and interactions between them using the concept of a vibrating string. Frenkel finds this interesting because it uses one guiding principle to describe a variety of phenomena. String theory has given mathematicians a lot of food for thought, but it currently balances itself in 10 dimensions rather than 4, which is not helpful for understanding our own universe. Frenkel notes that as a mathematician, he sees all spaces as equal and loves string theory for what it has given them. However, he notes that it might not be a correct theory for understanding our reality, and it might only apply to a 10th dimensional reality in some other universe. Edward Frenkel talks whether current theoretical physics can lead to a better understanding of reality. Frenkel expresses doubt, but also acknowledges that with some modifications and new ideas, it could be possible. Frenkel references Richard Feynman's quote, "There is no doubt that your theory is crazy. The question is whether it is crazy enough to be true." The conversation transitions to discussing Eric Weinstein's attempt at a theory of everything called geometric unity, which Frenkel finds original and beautiful. However, he also expresses his belief that the pursuit of a theory of everything is counterproductive and not feasible. Frenkel argues that the concept of a theory of everything is an ego trip for some physicists, particularly men, and that there are better ways to motivate scientists. Frenkel also notes that some theories are better than others, and Eric's theory has a unique approach to producing some of the elementary particles that we observe. In this section of the Lex Fridman Podcast, mathematician and physicist Edward Frenkel discusses the challenges of developing a theory of everything, specifically in the context of quantum field theory. While quantum field theory can describe physical phenomena with great accuracy, it is still incomplete and lacks a rigorous foundation from a mathematical perspective. Frenkel explains that a new theory may be able to explain new phenomena, but it would still be incomplete if it is not mathematically rigorous. Frenkel also describes the search for a simple equation that governs the universe, like the ones that he is developing in his new strand of the language program, and indicates that such equations may exist. However, he acknowledges that the search for simplicity may be driven by our own desire for it, and that there may be a more complex reality at play. He goes on to discuss the differences between working inside academia and outside of it, highlighting the limitations and benefits of each. Frenkel recognizes that being part of the academic community provides security and access to brilliant people and collaborative opportunities, but it can also be limiting due to the expectations and constraints within the community. Frenkel points out that academia has been historically designed to deal with the insecurity and imperfection in human scientific endeavors. He also mentions that academic culture is a human activity, and therefore, it has its share of good, bad, and ugly elements. With AI making changes to the way we approach education, the role of universities in the next 10, 20, 50, or 100 years is up for debate. Frenkel references Einstein, who initially attempted to become a university professor but ended up working as a patent clerk instead. They touch on the rare instances where people have made tremendous advances outside of academia, citing examples such as Yitung Shang. However, Frenkel highlights the prohibitive cost and great degree of concentration that math and theoretical computer science require at the top level, making it challenging to succeed without being connected to the university system. The conversation then moves towards how to think deeply and achieve a state of mental and psychological concentration required for the top level of math and theoretical computer science. Frenkel notes that it is a deliberate process that requires sustained effort, but the moment of discovery is often unpredictable and cannot be done by will alone. He likens it to the Eastern concept of satori, or enlightenment in Buddhism, where you have to relax to let it come to you. He then explains the nature of mathematics as a discipline. He describes it as a very stringent set of rules where everything needs to be proven, unlike other disciplines like physics where arguments are often intuitive and not rigorous from a mathematical perspective. He gives the example of Andrew Wiles' proof of Fermat's last theorem and describes it as a lonely and frustrating process where you feel close to solving the problem, but there is always one stubborn thing that doesn't compute. Pierre de Fermat, a French mathematician, claimed to have solved it in the 17th century but left no proof. For 350 years, many mathematicians tried and failed to prove it until Wiles in 1994 announced a proof, but a gap was found later, nullifying the whole thing. Frenkel praises the collaborative effort of Wiles and his former student Richard Taylor in finally closing the proof in 1995. In this section, Edward Frenkel discusses the proof of Fermat's last theorem by Andrew Wiles and Richard Taylor. He explains that Wiles and Taylor actually proved a statement called the Shimura-Taniyama-Weil conjecture, which is equivalent to Fermat's last theorem. Frenkel also provides a simple explanation of Pythagoras' theorem and uses it to explain Fermat's last theorem, which states that the equation x to the power of n plus y to the power of n equals z to the power of n has no solutions in natural numbers for n greater than 2. He notes that this deceptively simple statement took 350 years to prove and that mathematicians often try to prove it because it is so easy to formulate. In discussing Wiles' process, Frenkel suggests that the experience of working on a problem for a long time with intense focus is common to many mathematicians. Frenkel notes that realistic theories of physics are about 3 dimensions or space-time dimensions, but mathematically, there is an interest in theories of 10, 11, 25, or infinite-dimensional spaces. However, mathematicians don't have the satisfaction of confirming their theories through experiments with big machines like the Large Hadron Collider. They prove things using rules of logic instead. Frenkel believes that mathematics is one half of the core in understanding the universe, while love is the other half. He is suspicious of theories that state everything can be explained through mathematics alone. Mathematics gives you tools and clear vision, but it can't provide a harmonious and balanced life. While mathematics can help one to discern patterns and find regularities in the universe, Frenkel emphasizes that it can generate things that are beautiful but can't explain why they're beautiful. It helps to explore the mind as much as it explores the physical world around us, and it sharpens our ability to understand beauty. The discussion then moves to Einstein's general relativity theory, which tells us that space-time isn't flat. Frenkel notes that this idea is deeply entrenched in us, but experiments have confirmed that light bends around a star due to the force of gravity, which is actually the bending of space-time. The curvature of the space-time dimensions is responsible for the force of gravity, and it's not just the curvature of spatial dimensions. When time is thrown into the equation, it curbs the space-time dimensions, which is responsible for the force of gravity attraction between objects. Edward Frenkel shared his experience of solving his first mathematical problem and the emotions associated with it. He explained that it was a technical problem given to him by his mentor, Dmitry Fox, when he was 18 years old and studying in Moscow. He expressed the excitement that came with the confidence of having an idea and the fear of not having what it takes to solve the problem. Frenkel recalled losing sleep while working on the problem and how it became a wake-up call to take care of himself. He remembered the moment of discovering a solution, which was surprising and beautiful, and how he saw a pattern that governed all the homology groups and spectral sequences in his work. He exclaimed that he had something that nobody else in the world had, and it was a strange feeling of possessing something meaningful and real that he did not share with anyone at the time. Frenkel did not worry about the possibility of someone stealing his solution as he was focused on the discovery and sharing it with his teacher. Frenkel acknowledges that there have been famous cases where people have been accused of stealing each other's ideas or not allocating credit enough, creating psychological stressors on young minds. He believes that the first step to address this issue is for the academic community to admit that they are human beings with both good and bad qualities. However, Frenkel notes that there is no systematic effort to create rules and ethics in mathematics to clearly define what is fair game and what is not. He states that many people just pretend that these issues do not happen or occur in isolated incidents, but Frenkel believes that it happens much more often than it should. Frenkel also discusses the unique problem of mathematics where young minds with fresh ideas and brilliance work closely with exceptional world-class scientists who may be corrupted with fame, money and recognition. Frenkel notes that there is no clear strategy or rules in academia on how to deal with this mix, resulting in a clash of new and old ideas. He also acknowledges that there is a lack of self-awareness and taking responsibility in the academic community. Frenkel says that the path to solving this issue is through more self-awareness and taking ownership of one's personal actions. Furthermore, Frenkel explains that the field of mathematics is more insulated from society and draws in very specific psychological types. He shares that he turned to math as a refuge from the cruelty and discrimination he experienced when he applied to Moscow University at 16 years old. Frenkel emphasizes that mathematics needs to break this cycle, and he wrote his book, Love and Math, to show the beauty of the subject to bring in new blood and different psychological types, including women. He hopes that by doing so, the academic community can shift from a vicious cycle to a virtuous circle of inspiration and collaboration. He also discusses the influence of his Russian background and cultural sensibilities, which he attributes to his fascination with both math and the human experience of love. Frenkel notes that his sensitivity towards romantic ideals in mathematics is a product of his life experiences, including his upbringing and the challenges he faced as a student in the Soviet Union. He discusses his experience with applying to Moscow University's mathematics department, where he faced anti-Semitic policies and had to overcome significant obstacles to achieve his aspirations. He shares how, during his entrance exam for Moscow State University, he was singled out as the only undesirable candidate and subjected to unfair questioning. Frenkel mentions that his nationality was listed as Russian, based on his mother's ethnicity, but this did not help him to avoid discrimination. He had to eventually attend the Institute for Oil and Gas Exploration in Moscow, which had a program in applied mathematics. Frenkel reflects on his initial denial of the impact of this experience, until he met a boy who had the same experience and died of the crushing blow. This realization led him to reflect on his experience in a more emotional and personal way, which he documented in his book. He talks about how writing from the perspective of his childhood self helped him to connect with readers and finally process his experience. Frenkel explains that he was not ready to acknowledge the cruelty and unfairness he faced as a child, and instead developed a defense mechanism of working harder and ignoring the pain. However, he eventually faced his trauma and allowed himself to reconnect with the child that he had neglected. Through this process, Frenkel was able to tap into his intuition and imagination and discover new dimensions of himself. He emphasizes that revisiting childhood trauma is a subtle and personal process that must be approached with caution and strength. Frenkel also notes that childhood trauma is a universal phenomenon that is important to acknowledge and address. Frenkel shares that he did not have professional therapy support during a difficult time in his life, but instead received help from close friends who held his hand through the experience. The conversation then shifts to Frenkel's personal loss of his father, and how his father's experiences in life shaped his own path. Frenkel learned that his father's experiences and struggles helped shape him and his own successes, and that his father's gift to him was his pride in his accomplishments. He describes how being faced with the intense love that he felt for his father following his death was incredibly painful, but also allowed him to learn more about what love and life really mean. Frenkel believes that gratitude is a crucial aspect of experiencing the human condition, and that love is the glue that holds everything together. He also acknowledges that while science can talk about love from different perspectives, the experience of love itself is beyond what can be put into words or concepts. Additionally, Frenkel expresses his respect for people like Ray Kurzweil who are working towards creating computer programs that can simulate the experience of loved ones who have passed away, as he believes that we all have a desire to reconnect with those we've lost. Frenkel states that he would give anything to have his deceased father back, but he questions why humans hold on to things and if it is possible to just let go and enjoy life as it comes. He references the Buddhist idea of just letting go, and sees holding on as an impasse because everything has a beginning and an end. Edward Frenkel then discusses different perspectives on understanding the universe and the concept of time. Frenkel notes that some individuals claim to have other ways of experiencing the universe beyond traditional understanding, citing examples of when time seems to stand still in moments of deep absorption, passion, or creativity. He suggests that this experience of being fully present in a particular moment may be the closest we come to understanding the fundamental truth of existence. Frenkel acknowledges that the human mind constructs narratives and memories around these moments, but questions whether our experience of time and free will are illusory. He suggests that we may need to step outside of our mind to see reality from a more all-encompassing perspective, and wonders about the more honest way to look at things. However, he notes that humans seem to like playing with time and the subjective nature of memory and experience, possibly driven by some aspect of evolution. Frenkel explains that many great scientists have described feeling like children when making their discoveries, and that preserving that childlike curiosity, fascination, and vulnerability is essential to scientific discovery and creativity. He acknowledges that it can be difficult to maintain that connection and spontaneity in a society that values hierarchy and formal education. Frenkel suggests that there is a balance between acquiring knowledge and preserving the innocence and curiosity of children. They also bring up the topic of artificial intelligence, AI, and how the perspective of creativity and inspiration challenges the idea that everything can be explained by computation and accumulation of knowledge. Fridman and Frenkel discuss the idea that the child's ability to create is not solely based on accumulated knowledge, but rather their inner child's perspective. Frenkel also notes that the evolutionary process that created humans may be a form of computation that holds within it the knowledge of billions of years of life on Earth. However, he expresses doubt that this knowledge can be fully explained by the computational algorithms that we are aware of today. They state that any theory regarding consciousness or life must take into account factors that do not fit neatly into a computational narrative. He points out that while humans have the ability to be genuine and experience things authentically, a focus on computation and neural networks could deny humans the possibility of acknowledging this part of themselves. Frenkel also mentions that while objective arguments have more credibility in the scientific community, he is starting to question the value of subjective understanding and the first-person perspective. He argues that the observer is always involved in the observation, as demonstrated in quantum mechanics and Einstein's theory of relativity, and that perhaps taking our first-person perspective more seriously could lead to a deeper understanding of the universe. Frenkel quotes Pascal to emphasize the idea that there are infinitely many things beyond reason and logic, and suggests that denying the possibility of this side of humanity is limiting. He argues that believing that everything is known or that there is a single correct answer can lead to confirmation bias and prevent scientists from seeing beyond self-imposed limitations. Frenkel makes an analogy with the French literary movement, Oulipo, where writers impose specific constraints on their work to push the boundaries of creativity. However, he notes that the goal is to experiment and play with these limitations, not to deny fundamental aspects of language or reality. Frenkel recognizes the challenge that scientists face in accepting that there are things that may not be fully explained, but explains that doing so can lead to a greater appreciation for the value of paradoxes and ambiguity, which are often central to complex phenomena. Frenkel stresses that this is not to say that scientific explanations are not valuable, but rather that it is important to recognize that there may be limits to our understanding of the world, and that embracing these limits can lead to new insights and discoveries. Frenkel explains that the double-slit experiment is a concrete realization of the idea that depending on how an experiment is set up, different results will be obtained. Specifically, when shooting electrons through the double slit, an interference pattern is observed as if electrons were actually behaving like waves. However, if a detector is placed behind one of the slits to determine which path the electron went through, the interference pattern changes, and the particles behave like classical particles. Frenkel argues that because of our attachment to naive deterministic ideas from 19th century physics, our psyche is lagging compared to scientific progress. He refers to this as a self-imposed limitation and explains that it is also due to a lack of proper education in math and science. Frenkel believes that everyone knows that there is something mysterious about our physical reality but argues that we do not have the proper tools to talk about it rigorously. He highlights the importance of developing tools and education that allow us to discuss concepts such as free will and consciousness. Frenkel notes that Einstein had said that the most important thing in life is the mysterious, and that imagination is more important than knowledge. Frenkel shares that his own mathematical research is never linear and often involves making a jump or a leap, rather than collecting more data. He explores the idea of discovering new concepts, such as complex numbers or the square root of -1, and questions whether a large language model could ever make such a discovery, given that the current knowledge base denies the existence of such concepts. Frenkel uses the example of Girolamo Cardano, an Italian mathematician, who discovered the square root of -17 in the process of solving cubic and quartic equations. Although this number seemed strange at the time, it conveniently dropped out of the final equation, giving the correct answer. From a mathematician's perspective today, complex numbers are not mysterious, but rather a way to plot real numbers on the real line.